In this screencast, I want to review the overall structure of the data in the relational model, and then go on and spend some time talking about some of the basic operations and how they operate on tables. Recall that the data in the relational model is represented by tables, and each table represents a set of facts, and each row or tuple represents a specific fact about the organization that's being modeled, by which the database is used. The operations in the relational algebra are table-oriented. In other words, what do I mean by that? They take tables, operate on them, and then return tables. So a table is returned perhaps with a subset of columns or a subset of rows, or after some manipulation of the table. One of the things that we won't talk about until later are constraints on the table, namely that the entries in a column must be unique. That's for a particular attribute, which would be a key, what's called a key. Finally, because it's set theory, I want to emphasize that everything is unordered here. The columns are unordered, but they're named, so we know what data is in each column. Okay, and the tuples are also unordered. So this slide is a little bit more formal. It gives some formal definitions. Typically will represent the attributes. Remember, the attributes are the things that represent the entries in a tuple. The attributes will be represented typically by some uppercase letter. This varies a lot from textbook to textbook, and people use different notation, but typically this is what we'll be using. The number of attributes in the table, in other words, the number of columns, is typically referred to as the degree. When we write R equals these attributes, that's the schema of the relation. And then you can think of that as sort of the class definition of a tuple. So, for example, in the instructor table, we might have an ID field or attribute, a name attribute, a department name attribute, and a salary attribute. Those attributes would have different types, of course, depending on what sort of data represents that information. A relation, R, and typically we'll use lowercase for a specific table for an instantiation of a schema. R is a subset of all the Cartesian products of the different domains. So D are the domains of the different attributes. So in our example here, ID might be an integer. So D1 would be the domain of all the possible integers that could be used. So obviously the Cartesian product of all these domains is a large set, but we're just using that as to define what the potential elements are going to be. Finally, these values, once you have a value in a relation, that's called the relation instance, and that again is specified by a table. So an element T of the relation R is called a tuple again, and it's represented by a row in a table. The number of tuples in a table is called the cardinality of a relation. Now, we have to be careful about this. We're going to use cardinality later on when we talk about database design, and it will be a totally different concept than what we're talking about here. But for now, cardinality will just be the number of tuples in a table. So let's talk about some of the operators. The operators can be broken down into categories. The first set we'll talk about are set operations, which you're familiar with from your previous courses. And they're the typical set operators that you're used to, and they're all binary. The intersection, take the intersection of two sets, the union of two sets, or the difference of two sets. We'll talk about each one of these later. Then there are some unary operators. The selection operator, which picks off a subset of the rows. The projection operator, which picks off a subset of the columns. And a rename operator, which I won't talk about in this screencast, but I'll talk about later. Finally, we'll talk about the Cartesian product, and you've already seen that, but we'll talk about it in the context of tables. Now notice the unary operators are symbols for them are the Greek alphabet, and they actually fit in. Selection is a lowercase sigma, s beginning both of those things. A projection is a lowercase pi, and rename is a lowercase r, believe it or not, which is rho. So sigma, pi, and rho. So let's talk about the selection operator, sigma. Remember, it returns a subset of rows or tuples. Okay, so given this relation, which has 4 columns, just an abstract picture here of a typical what relation might be like with four attributes, and it also happens to have 4 tuples, 4 rows. Okay, now down here we have our sigma, and here's our relation R, and what we've got down here is a condition, and this condition is going to determine which rows we pick off. So the condition here is that A is equal to B, so that's saying the entry in column A should be equal to the entry in column B, and D is greater than 5. So that would be this one, not this row, and this row. So we want the rows to satisfy these 2 conditions. And if you do that, well, which rows are A equal to B for? The rows that A are equal to B are that row, not that row, and that row. Okay, and then which rows is it true that D is bigger than 5? That'd be that row, and that row, and that row. And so now you take the intersection of those 2 things, and you see that the intersection are these 2 rows. So that in general is how the selection operator works. You write it with a condition, usually denoted by C, that's down here, and then you just apply that condition to the rows of the table, and if it's true, then you put it in a table to be returned. The Boolean operators that we use are these, and you'll see the different notations. These are all notations for and, notations for or, and notations for not. I'm sure you've seen those in your other computer science courses. This next slide talks about the projection operator, pi, and again, we have a very simple example here. 3 columns now, A, B, and C, and with the following entries. And if we project R on its columns A and C, what we end up with is we would just take this part of the original table. That would give us this. However, we have to be careful, right, because rows must be unique. Remember, we're working with sets. And so since the rows have to be unique, these 2 entries over here collapse into this one. Finally, I want to talk about set operations. 3 set operations, in order to apply them, again, they're binary operators, so they work on 2 tables. In order to apply those operators, the 2 tables must be union compatible. In other words, they have to have the same schema. They have to have the same number of attributes and the same matching data types. So, for example, if we have these 2 relations, A and B, and A and B, A and B, this one is R, and this table is S, and we take their union, okay? Well, if you just take their union together and you look at it, there's a duplicate. A comma 2 is in, or alpha comma 2 is in both tables. So one of those gets thrown away, and basically we're left with 4 elements in the union. The set difference between 2 relations is you look at the elements in the first table, and then go through the elements in the second table, and any elements from the first table that you find in the second table, you remove. So basically, you're getting the elements in the first table that are not in the second table. That's shown down here. Elements in the first table, but not in the second table. And if you look up here in this example, alpha 2 appears over in S, and so alpha 2 goes away. Neither of the first row and the third row do not appear in S, and so what you're left with is 2 rows in this table. Note, this wouldn't make sense unless they had exactly the same schema, so they have to be union compatible. The next operation is set intersection, which I'm sure you're also familiar with, and now all we do is look to see which rows are in both tables. And in this particular example, again, the second row is the one in both tables, and so that a table with that single row is what gets returned. This is the definition that each tuple has to be in both tables. Note that, and you should work through this yourself, convince yourself that R intersection S is the same thing as first taking R minus S and then subtracting that from R. Finally, I want to talk about the cross product of two relations, the Cartesian product. Remember, the formal definition of Cartesian product is just you look at every pair, every possible pair of elements from the first set and the second set. So here, if we stop and think about what that's going to be, there are 2 elements in R, 2 tuples, and there are 4 tuples in S. So that means we have 2 choices for the first part of the tuple that we're going to form, and we're going to have 4 choices for the second part of the tuple. So that means we're going to end up with 8 rows. So the relation of R cross S is going to look like, well, one way to view it, remember there's no ordering here necessarily, but one way to view it is we're going to take this first row, alpha 1, and then we're going to match it with each one of the rows in S. And so we get alpha 1, and then we get alpha 10A, alpha 1 beta 10A from these two, and then we get alpha 1 beta 20B from this one, etc. And so you know right away that the cardinality, right, of R cross S is going to be the cardinality of R times the cardinality of S. So that's it for this screencast. This is just to get us going. In class, we'll try to answer any questions you have on any of this. Hopefully, a lot of it is, at least the set operations themselves are familiar with you. And again, I'll be happy to answer any questions, and I'll see you on Thursday.